Building a modern robot requires coordinating motors, sensors, and complex decision-making logic. Today, we are going to start assembling those pieces by writing your very first functioning robot software program. To do this, we use ROS, the Robot Operating System. Despite the name, ROS is not actually an operating system. It is a flexible software framework that runs on top of Linux, designed specifically to manage all of your robotic hardware and software. Looking at this diagram, we can see the core concept of the entire framework, the node. A node is simply a small, single-task program. Complex robotic behaviors happen by snapping dozens of these modular blocks together to share information. To build our first node and watch it exchange data, you will need a computer running Ubuntu, a basic grasp of Linux terminal commands, and some familiarity with Python. By the end of this session, you will write a complete talker node from scratch. Mastering this single publisher is a necessary first step. Whether you are reading from a laser scanner or sending commands to a motor, you will use this same messaging logic to make those components talk to one another. Step 1 is getting the software onto your machine. Open your Ubuntu terminal and run the command to add the official ROS Noetic repository to your system's package sources. Next, you have to tell your computer to trust that source. Set up your cryptographic keys to securely validate all the packages you are about to download. Now run sudo apt install ROS Noetic desktop full. This command pulls in the necessary libraries, simulation tools, and core system files. It is a massive download, so give it time to finish. Once the installation completes, initialize and update a tool called ROSDEP. This utility scans your intended build and automatically installs any hidden system dependencies your software needs to run. With ROS installed, you need a place to work. In this framework, all custom code lives in a dedicated directory called a Catkin workspace. Create a folder named Catkin WS with a SARC subdirectory inside it. Navigate into that workspace and run the catkin make command to compile your empty environment. Looking at this terminal output, you want to verify that the process succeeded. Check near the bottom of the log for the specific phrase build files generated. Your workspace is now an isolated sandbox. It protects your main operating system while giving ROS the exact folder structure it needs to compile your custom packages. Now we can structure the code. In your SARC folder, use catkin create package to build your new package. As this diagram shows, we explicitly pull in ROS.py and standard messages. These dependencies tell the system we are using Python and standard message formats. Navigate into your new package, create a directory called scripts, and make a new Python file named simplenode.py. Let's look at the script on screen. This line right here, rospy.init node, is where the program officially registers itself with the framework, requesting a unique ID so the rest of the system recognizes it. The next critical line is rospy.publisher. This establishes an outbound data stream, configuring the node to broadcast text specifically on a channel called the chatter topic. Finally, we wrap a loop around a log command. The script checks the time, builds a hello world message with that timestamp, and broadcasts it over the topic once every second until you force it to stop. The logic is complete, but writing the code isn't enough. Linux heavily restricts executable permissions by default, meaning the framework currently lacks the authority to run your script. If you try to execute your Python script right now, the operating system will block it. You must run the chmod +x command on your file to explicitly grant execution permissions. With the permissions fixed, step back to the root of your catkin workspace and run catkin make one more time so the compiler registers the new package. There is one final hurdle before launch. You must run source dev setup.bash. This updates your current terminal session's environment variables, so the computer actually knows where to find your compiled files. As this diagram illustrates, everything requires a coordinator. We use a command called roscore to launch the master node, the central communication hub sending out pings to manage all other active programs. To see how this looks in practice, you need a split setup. Start roscore in your first terminal. Then open a second window, source your workspace again, and trigger your code using the rosrun command. The master node handles the network addressing. Without it, your talker program would blindly shout into the void, completely isolated from any other software running in the system. Hit enter, and your terminal springs to life with a continuous data stream. Check the exact output. You should see a steady column of hello world messages. each tagged with a precise timestamp, confirming your publisher loop is executing perfectly. You now have a program successfully broadcasting data. The logical next step is writing a listener node, a subscriber designed to capture these specific messages and react to them. You have moved past the theory. By configuring your environment and registering this script with the master node, you have successfully integrated a Python program into the ROS framework.